Okay, so in this clip we're just going to summarize the splitting effects that we've seen so far and look at the three different versions, just summarize them in one place. And what we're going to do is we're going to look at a singular CH, so we're just looking at a peak with an integration of 1, and we're going to put that in turn next to 1 proton and then next to 2 protons and then next to 3 protons in the final example, and just summarize the three things in one position. So the first one, obviously, as we say, we're looking at the same proton in each example. We're going to look at the left hand singular proton attached to CH. Don't know what the other substituents are, but we know they're not hydrogens. So we'll look at this peak individually. So in the low resolution spec, remember, we would have just seen a singular peak with an integration of 1. However, we're now going to see evidence of splitting because of the adjacent protons to the proton that we're looking at. So in the first instance, it's next to 1 proton, and what we're going to see is that peak become a doublet of peaks. We're going to see in the second one that become a triplet of peaks, and in the third one we're going to see that singlet become a quartet of peaks. And what we've seen on the previous examples as well was that we would see the integration ratios of the individual little peaks within the split peak of that proton, and what we'll see is that the doublet will have an integration ratio of 1 and 1, the triplet will be 1, 2, 1, and the quartet will be 1, 3, 3, 1. Now, mathematicians amongst you will start to recognize those numbers as being lines from Pascal's triangle and various statistical models coming through that. But you see the first row next to 1 proton, and then obviously 1, 1, 1, 2, 1, 1, 3, 3, 1, etc. as we get more complicated down the molecule. And what we can see is that when we are adjacent to a singular proton, we get 2 peaks. When we're adjacent to 2 protons, we get 3 peaks. When we're adjacent to 3 protons, we get 4 peaks. And this is what's called the n+1 rule. So when you are looking at the integration ratios of a peak, which you've got in a molecule, so remember, the integration of all of these peaks in total are the same. The only thing we are seeing is the shape of the peak. So all of the green areas from the start to the finish of the peak, from the start to the finish of the peak, from the start to the finish of the peak, are all identical in all 3 examples because they are contributing to the integration of 1 proton. Remember, we are looking at that proton in each of the 3 examples. The splitting, i.e. the shape of the peak, whether it be a doublet, a triplet, or a quartet, that is due to the adjacent ones, and that is governed by the n+1 rule. So if you're looking at 1 proton and it is adjacent to 2 protons, you would see 2 + 1 or 3 peaks in that NMR region for the proton you are looking at.